This is a lesson on 2.3, the basic terminology and notes that you should take for 2.3, polynomial degrees or higher degrees with modeling. Students should be able to graph polynomial functions, predict their end behavior, and find the real zeros using a grapher or an algebraic method by the time you're done. So first of all, I'll talk about the vocabulary of polynomials. Each monomial in the sum shown, each monomial in the sum given here is a term of the polynomial. So basically what that's saying is each term in the polynomial is a monomial, if you remember that definition, where the n is a positive integer. Then a polynomial function written in this way with the terms in descending degree is considered to be written in standard form. So basically, when you write out your polynomial where the terms are written in order so that the degrees of the exponents are descending or getting smaller, that's standard form. All the a's with the subtext, the constants, they're called the coefficients of the polynomial. And then the term a sub n times x to the n is the leading term. And of course, you know a sub n is the leading coefficient then. A sub 0 is considered the constant term. It's the term that does not have an x on it. What we're going to do now is we're going to just go through an example of graphing transformations of monomial functions. So basically, I'll read the problem first. Describe how to transform the graph of an appropriate monomial function f of x equals a sub n times x to the n into the graph of h of x equals negative the quantity times the quantity x minus 2 to the fourth plus 5. We're supposed to sketch and compute the y-intercepts. Basically, what this is saying is you're going to take the function given that you're trying to graph, and you're going to compare it to its basic monomial function. That includes the leading coefficient. So what that means to us is we're going to compare this graph to the graph of negative x to the fourth. Well, without much work, you know x to the fourth would be a kind of a flattened out x squared. And then the opposite of that, well, this negative value here, that just reflects in the x-axis to bring us to this blue graph. And hopefully without too much work, you would remember if you subtract 2, that's going to shift it to the right 2, since it's in with the x. And then when you add 5 outside of the monomial function, you raise it up 5, which results in this red graph shown. So that's verbally what's going on. And then to find the y-intercepts, well, how have you always found the y-intercepts? You would plug in a 0 for x. If you plug in a 0 for x, the resulting answer will be your y value, so therefore it's your y-intercept. We should think, just from this graph, the y-intercept will be somewhere down here, and of course, without too much work, we find the y-intercept is negative 11, or the coordinate point 0, negative 11. These next diagrams are basically just here to show you so that you have an idea of what to expect for the cubic and quartic functions. Basically, if your leading coefficient, whatever the function is for whatever the cubic function is, if your leading coefficient is positive, you could have different looking graphs. They could look um, so if it's positive, if the leading coefficient is positive, you could have your basic function x cubed, as shown here, or you could end up having a function that still rises or starts the same way as the first one, but then will have a maximum, a minimum, and then still ends the same way as your basic function ended. Just realize you could have this action going on in the middle. If the leading coefficient is negative, you have just the opposite. It would start up high and fall to the right, sometimes having a minimum and a maximum in between. But the end behavior would still be the same. With a quartic, or x to the fourth graph, you could have your basic graph x to the fourth, as shown here, or you could have other things happening in between, just as long as the end behavior still is the same. When the leading coefficient is positive, your end behavior will be that it will end up approaching infinity to the left and infinity to the right, no matter what happens in the middle with mins and maxes. If your leading coefficient is negative, the opposite happens. As you go to the left, your end behavior is going to approach negative infinity, no matter what happens in between, and as you go to the right, your end behavior will approach negative infinity as well. Again, no matter what happens in between. What you need to know is what could happen in between, and that's what I have written next here. The local extrema and the zeros of the polynomial functions can be determined in this, or will range in the following way. A polynomial function of degree n will have at most n minus 1 local extrema. They don't have to have any, but they'll have at most n minus 1 local extrema. And they'll have at most n zeros. Well, you can see that up here. If we're talking, the cubic function could have, the basic cubic function, x cubed, where n equals 3, could have at most n minus 1 extrema, so 2 extrema. Well, in this case, there's no extrema. In this case, there's 1, 2. Okay? With the quartic function, well, quartic, the basic function would be x to the fourth, so n minus 1 would be 4 minus 1, which is 3. That is, it could have at most 3 extrema. In this case, it could have 1, it could have 3, or it could have, well, there's 1 again, and so on. We'll talk more about even more restrictions, but what you need to focus on is at most how many it could have. As far as the number of zeros go, consider putting the coordinate grid anywhere on any of these graphs. The number of zeros that a function could have is at most equal to the degree of the polynomial. So if I put the graph right here, well, there's going to be 1, 0. If I put the graph right in the middle here, I could have 1, 2, 3 zeros. If I put the grid down here, well, I would have at most 1, 0. Or I would have 1, 0, excuse me. So that's what this part is saying. At most n number of zeros, or x-intercepts. What this next note is talking about is a way for you to tell for any polynomial function what the end behavior is going to be just by looking at the degree and the leading coefficient. Here's what you need to know. If what I would do is if I were you is I would compare or think about the basic function you can relate to the graphs that I'm discussing. So what I'm going to talk about is an odd degree polynomial first. Now, for an odd degree polynomial, what's your basic function you might think of? X cubed. But you know what x cubed looks like. It looks like this. As you approach negative infinity, the limit as x approaches negative infinity of this function equals negative infinity. It goes down. As you approach positive infinity, it goes up. Every odd function with a positive leading coefficient will have that same end behavior. That's what you need to remember. If you look at this function here, it's still odd, but it has a negative leading coefficient. So just think of negative x cubed. Well, that's going to look like the function, the basic function that you already know about. Its end behavior is going to be the same as the end behavior for any odd polynomial with a negative leading coefficient. That's what you need to remember. The same is true for even functions. Just think about the basic function you know, a parabola. If it's an even polynomial with a positive leading coefficient, it will have the same end behavior as a parabola. As you go to the left or to the right, you'll approach positive infinity, just like y equals x squared. If it's an even function and a negative leading coefficient, it's going to be just like y equals negative x squared, which you know opens down. Ignore that line that just showed up there. I'll say that again. If you have a parabola opening down, or if you picture that in your head, any even polynomial with a negative leading coefficient will have the same end behavior. As you go to the left, it'll approach negative infinity. As you go to the right, it'll approach negative infinity. It's the same for all of them. So we can take a look at an example here. Describe the end behavior for this g of x. Well, it's a polynomial. So all I'm concerned with is that the leading coefficient is positive, the power is even, just like y equals x squared. So it's going to have the same end behavior as that. I know that end behavior. It approaches positive infinity in both directions. So all I would have to do is say the limit as x approaches negative infinity of the function is positive infinity, and the limit, well, my computer cannot keep up with me today, as x approaches positive infinity of that same function is also going to be infinity. Done. Didn't even need to graph it. There are multiple ways you can find the zeros of a polynomial function. You can factor. Algebraically, if you can factor, do it. I notice every term here has an even number and an x in it, so I'm going to factor out a 2x. Once I do that, what I would do is try to factor the, in this case, quadratic that's remaining. Pretty quickly, you should realize x minus 3, x plus 1 is what that would factor into. If you're finding the zeros, you set it equal to 0, and then tell me what would work. X equals 0, x equals 3, x equals negative 1 would be your 0. The multiplicity of a 0 of a polynomial function is basically says if you can factor out the same binomial more than one time, however many times you can factor it out, that means that 0, like in this case c would be the 0 of this factor, that 0 would have a multiplicity of m. However many times you can factor this out, that 0 has a multiplicity of m. What this next statement is saying right here is basically if in a polynomial function, if it has a real 0 c of odd multiplicity, so if it has x minus c as a factor an odd number of times, then the function will cross the x-axis at that 0. So if, let's say, this was where c was, and it just factored out one time, you would cross the x-axis at that spot. If that c was of even multiplicity, so you could factor out an x minus c 2 times or 4 times or so on, then the graph would not cross the axis. That could be the example where if it was that same c value, maybe it came down, it would hit, but then come right back up again. So that would be where there's no sign change at c. That's what this is describing. So if you're trying to sketch a graph, if you have the polynomial factored, what you would first do is you would plot the zeros. So you've got a 0. If x plus 2 is a factor, you would plot a 0 at -2. I've already got the graph drawn here, but this gives you an idea. I'd plot the 0 at -2. And then there's another one at a +1. I also, let me just reveal what I've just said. So, yeah, so then, I'll just reveal it all. What I would do next is I would look at the multiplicity. X plus 2, okay, that's where the c value was -2. It's got an odd multiplicity, which means it's going to cross the axis there. This has an even, which means it's going to touch there, but not go through the x-axis. I also see that we have 3, 4, 5 total exponents here, if I add them together, which means it's an odd function. Since it's an odd function, and the leading coefficient is positive, I know it's going to start down here. I could also very easily find the y-intercept by plugging in zeros for the x's and get that point plotted. Well, now from there, I would know I start down, I cross at -2, I know where to cross the y-axis, and at some point I've got to come back down. I'm going to hit x value of 1, and I have to come back up. Whatever you do in between here, here, and over here doesn't matter. I don't care if you don't know where the peak is and so on. All I care about is having those main points.